Welcome to a lesson with Dr. Powell. Let's look at the idea of sequences. And what a sequence is? A sequence is like a list, like 7, 10, 13, 16, 19, so forth. Now, a list actually can be thought of as a function. Think of an XY table where we have X and Y. So these are outputs and inputs. What would they be? Maybe we could say like, this is the first thing in the list. So maybe it's the first position, the second position, the third position, the fourth position, fifth position, and so forth. Naturally, any list can be thought of as a function in this way, where the input or the domain are simply whole numbers or counting numbers like this, representing the ordinal position of where we are in the list. Now, notation, usually we don't use X and Y. Usually we use N for natural counting number. And here we could say like a function, this is not A, it could be any letter, F, B, whatever, but we usually use A here, like A of N for function notation. However, we don't even usually do that. Instead of saying A of N, we usually say A sub N to really emphasize that this is a list that we're dealing with, and the function corresponds to a list with a domain being whole numbers. So this is kind of how we would begin thinking about it. Now, in this particular case, notice that for every run of 1, we have a rise of 3 in the output. And that means this has a constant slope. Not all sequences have constant slopes like this, but this one does. If it does, it's called an arithmetic sequence. So if it does have a constant slope, we could think of, writing a formula for it, where from output to input, and it's linear. So we could think where this is the intercept, namely the output when X is 0. And this right here is the slope. So this particular case, we know the slope is 3 over 1, which is just 3. We can replace our X with N, our Y with A sub N, and our intercept, well, we have to know what it would be at 0 when N is 0. So we just go backwards. So we're adding 3 every time. We go back to 4. So then we would know our intercept would be 4. So this right here, A sub N is equal to 3n plus 4, would be a formula for our sequence. So we have N being an ordinal position, we plug it in and we get this out. Now, also, we can think about a graph of this function, but remember that the domain are just points like 0, 1, 2, 3, and so forth. So that's the domain. So that's what we can plug in. So we're just going to get something pixelated. The intercept is at 4, and then we go up just to say that's up 3. Let's just kind of skew our coordinate, our axes a little bit. So we add 3 and we'd be right there. Add 3 more and we'd be right there. And let's see, and we'll start right there. So it's going to look like, so the graph of the function is actually going to be this one that I'm hopping between right now, just going up. It's just going to be dots going up. So this would be how we could think about this particular sequence as a list. Okay, let's look at another example of a sequence. Perhaps we have something like 8, 4, 2, 1, a half, a fourth, and so forth. So this is a sequence, A sub N. We can come up with a formula for it. And we can do this in various ways. One way, perhaps, is we could just let the first guy start at 0. And when you let the first guy start at 0, it actually makes it pretty simple. Like in the last case, you know how we went backwards to get the intercept? Well, we don't have to do that anymore if we just start our counting at 0 instead. 0, 1, 2, 3, 4, 5, and so forth. Then let's think about a nice formula for this. So this looks like, well, what's happening? Looks like we're multiplying by a half every time, right? So when we multiply by a half, so we're multiplying by the same thing every time. Such a sequence, when we're multiplying by the same thing every time, instead of adding by the same thing every time, this time is called geometric. Geometric sequence is when we multiply by the same thing every time. And an arithmetic sequence was like the last one, where we added by the same thing every time. Okay, so let's take a look and go back to what we're doing here. And let's see if maybe we can come up with a nice formula here for this particular sequence. This is a geometric sequence. So it's going to be of the form, it looks like, since we're multiplying by the same thing every time, this is like exponential growth or decay, because we're multiplying by the same thing we're multiplying by is by a half. We're starting at 8, and then 1 later we're down at 4, and then we're half of that. I mean, it looks like it's like on an exponential curve going down. So it's going to be of the form, instead of mx plus b, you can think of it as the form m to the x times b, where b is really usually written out there, b times m to the x, where multiplication has become an exponentiation, addition has become multiplication. So so it's just an exponential function. B is the intercept where you start, well, 8, and you can check it out when you throw in a 0, that's just 1, so it's just the intercept. So this would be the intercept, 8 times, kind of like m is now multiplication, so multiplying by that every time you add 1 in the input, so times 1/2 raised to the n. And that would be a nice formula, very simple to write down, just based upon this simple description and ideas. This is an example of a geometric sequence. So where we're to get from one term to the next. So in particular, how do you get from an to an plus 1, just one further in? Well, what is a sub n plus 1? That's when you plug in n plus 1 in for n here. And so then you would have 8 times a half to the n plus 1, and 8 times a half. So how do you go from here to here? Simply, oh, this is an n, excuse me, it's the n. Well, simply to go from an exponent of n to an exponent of n plus 1 means you've multiplied by half. So if you multiply by half, that adds 1, that adds the exponents together, so that you get n plus 1. So really it's just multiplication by half between each term, even given the formula. Okay, so this is just a first little video introduction with a couple examples of sequences that we can see. Thanks for watching.